These are notes on intermolecular forces, which are found in Chapter 8, Section 4 of your book. So there are three types of intermolecular forces that we're going to talk about in this course. And when we talk about intermolecular forces, inter meaning between, molecular is molecules. So we're talking about the forces that exist between molecules. So if you think about states of matter, liquids, solids, and gases, you know that there's some sort of force holding molecules together in solids and liquids to a lesser extent, but not in gases. In gases, molecules are free to fly around independent of one another. And the three types of forces we're going to be talking about in this class are dispersion forces, dipole-dipole forces, and what we call hydrogen bonding, which you probably talked about last year in biology. Just to recap though, hydrogen bonding isn't a bond, it's just a force. So it's called hydrogen bonding, but it's not an actual bond. A hydrogen bond, which is the strongest of these three forces, is only about 2 to 5% as strong as a covalent bond. So please don't confuse the two and think there's an actual bond going on in hydrogen bonding. So let's break these down. Dispersion forces, first of all, are experienced by all molecules and atoms, and they result from the shifting location of electrons in an atom. So all molecules and atoms have electrons, and so all molecules and atoms experience dispersion forces. So here's an example here that I can show you. This is the helium atom, and helium, as we know, has 2 electrons. Now, at any point in time, those 2 electrons can be evenly spaced, say on this side and this side, or here and here, but they could also be unevenly spaced, such as they are in this case. So here we've got the 2 electrons closer to this side of the atom than this side, which is going to give this side of the atom a partial negative charge, and it's going to give this side of the atom a positive charge. So you get, here, let me see if I can write the little deltas in here. So you get a dipole. It's not a permanent dipole though, it's what we call an instantaneous dipole, meaning it's just there in that instant, because then the electrons may move in a different way, which would change that dipole. But that instantaneous dipole, in that moment, if this helium atom is near this helium atom, that can then induce or create a dipole on a neighboring helium. So because this helium now has a positive charge here, the electrons from this helium atom may be attracted over towards this, which would cause an instantaneous dipole on this helium atom. And then that would also cause these 2 helium atoms to be attracted to one another. They would experience an intermolecular force. Now, this isn't limited to 2 atoms. You could have 5 atoms or 6 atoms or 6 molecules even. It's could be molecules or atoms. So this is one of the intermolecular forces, dispersion forces. And you can think of it as it's caused by the dispersion of electrons in an atom or molecule. So let's look at differences in dispersion forces, okay? So one of the things we could look at is the molar mass of atoms, okay? So let's say that the higher molar mass is going to equal greater dispersion forces. You can think about it this way. Something with a higher molar mass is going to have electrons that are further away from the nucleus, and I'm going to give you an example of this. And so they're more susceptible to an instantaneous dipole from a neighboring atom because they're not bonded as tightly to the nucleus. So let's look at an example with the noble gases. So here we have the noble gases from helium on down to radon. And if you notice, here helium has the smallest molar mass, right? And then radon's got the largest molar mass. So from helium, right here, on down to radon, we get increasing molar mass and increasing principal energy levels too. And then on the x-axis here, we have boiling point. And so helium has the lowest boiling point because it's going to experience the least dispersion forces. Radon, which has the higher molar mass, it's going to be greater dispersion forces, so it's going to have the highest boiling point. In other words, it's going to stay liquid where there needs to be some intermolecular forces with the least, for the longest amount of time, or for the largest input of energy. Because it has the greater dispersion forces, so it's going to be more likely to stay together. The atoms will be more likely to stay together in liquid form than to fly off on their own. Alright, let's look at something else, because this obviously has to do with single atoms. I chose noble gases because they all can exist as single atoms. You can also look at molar mass of compounds, but there it gets a little more complex. And the reason for that is because the shape of the atom actually is going to influence the dispersion forces, which will then influence something like the boiling point. So, area for interaction. A larger area for interaction equals greater dispersion forces. So, you can think about it as the larger area that the molecules have to interact with each other, the greater the force between them, the greater the ability for a force between them. So let's look at an example of that. So for example, let's look at 4 what we call alkanes, but 4 covalent compounds. Methane, ethane, propane, and butane. And you've heard of all these. We talked about them a little in covalent naming. Ane means it's all single bonds. Meth means 1 carbon, so methane is CH4. And you guys should be familiar with the shape of that because we had it as one of our examples. Ethane, eth means 2 carbons, so that's C2H6. Pro means 3 carbons, C3H8. Bute means 4 carbons, C4H10. And if you look at their boiling points, you notice that methane has the lowest boiling point, and then the boiling points increase as you go down the list. So the more carbons you have, the higher the boiling point is, meaning the greater the dispersion forces. So let's look at what those look like. These are pictures of all of these. Now they're 3D pictures, so for example, this is methane right here. You'll notice it looks like there's only 4 hydrogens. In fact, you should recognize this shape as tetrahedral. It looks like there's only 3 hydrogens, but this shape is tetrahedral, so the 4th would be kind of back there in the screen. So that's why if you counted up, the hydrogens are going to look a little different because these are kind of 3D. But you'll notice if you have 2 methane molecules, interacting with each other, that they can interact, over about this much area. But if you have 2 ethane molecules, that's a much larger area that they could interact over. If you have 2 propane molecules, it's larger still. And if you have 2 butane molecules, of the 4, that would be the largest. So there's a much larger area for interaction if you had 2 or more of these, meaning there's a larger ability for dispersion forces to affect the next molecule over. So larger dispersion forces, you're going to have a higher boiling point because they're going to be more likely to be attracted to one another, less likely to fly off on their own. Which, by the way, that attract to one another is in liquid state. Fly off on their own would be in gas state. And there are, you could look up boiling points of, if you wanted to, boiling points of alkanes, and there's more than just 4 of them. There are lots and lots and lots. And obviously that chain is going to get longer and longer each time, and we would expect that boiling point to go up and up and up each time. Until you get into, this is obviously still negative temperature. However, the next one up, pentane, actually has a positive boiling point, which means it's above water's freezing point. Water's freezing point being 0. And you may even be able to find some alkanes that are liquid at room temperature. You would expect those to have lots and lots of carbon, so it's a very long chain. So the next one we're going to look at are dipole-dipole forces. So these are experienced by all polar molecules. And what they result from is a permanent dipole interacting with another permanent dipole. So unlike before when we were talking about, well, let's say this, the examples I gave you before, so if we go back a page, none of these experience permanent dipoles, right? So the atoms over here, these are all atoms. They don't experience permanent dipoles. And these are all nonpolar, so there's no permanent dipoles. We're talking about instantaneous and induced dipoles. But now we're talking about molecules that have permanent dipoles, such as HCl. Now, one thing to note before we move on, though, is that something like HCl, which is going to experience dipole-dipole forces, which are obviously stronger than dispersion forces because these dipoles are permanent, HCl, because it has electrons, is also going to experience dispersion forces. So simply because something experiences one of these three, dispersion, dipole, dipole, or hydrogen bonding, doesn't mean they don't necessarily experience the others. So something that experiences dipole-dipole forces also experiences dispersion forces. So I think especially after understanding dispersion forces, it's easy to see how a dipole-dipole force would work. Because as we know, in HCl, here on the hydrogen side, we end up with a positive charge, and here on the chlorine side we end up with the negative charge, and then another HCl is going to have a positive charge on this side, and this is going to have the negative charge on this side, and so that positive and that negative can interact with one another, and that is going to cause what we call a dipole-dipole force. Now, this, as we said before, don't confuse these forces with bonding. So the covalent bond between the hydrogen and chlorine is very strong. The intermolecular attraction between the hydrogen and chlorine is very weak. That's why when hydrochloric acid boils and goes from a liquid to a gas, the hydrogen and chlorine in an individual molecule stay together. It's this force here that's broken apart. It's that attraction. Almost you can think of it as Red Rover, okay? And, we all played Red Rover rather violently as children. And you're holding the hand of the person next to you. That's like an attraction, but that can be broken pretty easily. When you do Red Rover, you end up breaking apart one person from another. You don't end up breaking apart a person. It would be very disturbing for children, but very odd if, somebody's arm broke off and it was left holding the other person's hand. So like a person ended up separating at their shoulder. That would be like separating the hydrogen from the chlorine here. That's a very strong attraction, whereas this is very weak in through here. So let's look at differences in dipole-dipole forces. Obviously, the stronger the dipole, the stronger the dipole-dipole forces. That makes sense. But you have to remember, all molecules also experience dispersion forces. So think about control variables. When you're comparing two molecules, you've got to compare two molecules that are pretty equally shaped and have pretty equal molar masses. You can't go comparing two radically different molecules because that's going to be affected by dispersion forces as well as dipole-dipole forces. So the two I chose to compare are ethane here, which is C2H6, and fluoromethane, which is CH3F. And so you can see they have relatively the same shape, they're relatively the same size. Obviously this one has fewer actual atoms, but fluorine compared to carbon is actually has a greater molar mass, and so that kind of takes care of the fact that we're missing the 3 hydrogen here. And you'll notice ethane is nonpolar, and it's got a boiling point of 184.5 degrees Kelvin. Kelvin is related to Celsius. And so if you're not familiar with the Kelvin scale, 0 Celsius is 273 Kelvin. we'll talk more about that a little later. Compare that to fluoromethane, which clearly has a dipole. It's clearly polar, because here we've got fluorine instead of another carbon with 3 hydrogens. So fluorine, we know, is our most electronegative atom, and so this ends up with the negative charge, and this side ends up with the positive charge. And so notice that boiling point is more than 10 degrees higher than ethane, even though they have about the same molar mass and they're about the same shape. It's that permanent dipole that's responsible for the dipole-dipole forces, meaning it's going to have a higher boiling point. It's going to be more likely to be attracted to itself than it is to go flying off, or it's going to take more energy to get it to go flying off than it will with ethane. So now let's look at hydrogen bonding. I want to reinforce again that hydrogen bonding is an intermolecular force. It's not a bond. Again, hydrogen bonding is only about 5% as strong as your average covalent bond. So it's experienced by molecules in which hydrogen is covalently bonded to a small, very electronegative atom, such as nitrogen, oxygen, or fluorine. And it results from the large dipole due to differences in electronegativity. So obviously, something that has a much larger difference in electronegativity, it's going to have a larger dipole, so you're going to have a larger force there. But it also is affected by how large the bonded atom is. So it's got to be small. So if you look at your table of electronegativity, you'll notice that there are other atoms that have the same electronegativity, say, as nitrogen. Chlorine, for example, and nitrogen have a very similar electronegativity. Chlorine on the periodic table, if you remember, is kind of right below fluorine. And so you would think that if chlorine bonds to hydrogen, it too would experience hydrogen bonding. But chlorine is so much larger than nitrogen, oxygen, fluorine. It's in the second energy level, and it even has p orbitals in there. And so it doesn't experience hydrogen bonding. Why? What does the size have to do with it if you're still going to get a large dipole? Well, what it has to do with is the fact that if hydrogen is bonded to a small atom, such as nitrogen or oxygen or fluorine, the next molecule over can get really close in because those atoms are so small. But if you have something like chlorine, then the next atom can't actually get as close in. And so hydrogen bonding is actually the strongest of the 3 forces. So it goes dispersion forces, dipole-dipole forces, hydrogen bonding. Sorry about that little glitch there. So the most famous, I would say, hydrogen bonding example is in water, which is why water has such a high boiling point and a high melting point, which is why it's so nice that our Earth is predominantly water. That's really what helps us sustain life. You know, we talk a lot about how we're 75% water and our Earth is 75% water, but the fact that water is 2 hydrogens bonded to an oxygen is what's responsible for water having a lot of the properties it has that makes it so useful for life. And so here's an image of the oxygens and the hydrogens. We've talked about water being polar, and so you can see how this would work, this hydrogen bonding, on a scale with 5 water molecules. So let's look at a hydrogen bonding comparison. So here I've got 2 different molecules, ethanol and methoxymethane. And don't worry so much about the names of them. I think we did talk earlier about things with an OH group are alcohols, and so that's why this is ethanol. So eth meaning the 2 carbons, C2, and then the ol for the OH group, which is what makes it an alcohol. Don't worry about the methoxymethane as far as the name. But what you should note is that both of these have the exact same number of atoms. So and the same type as well. So they both have 2 carbons, they both have 1 oxygen, and they both have 6 hydrogens. So they've got the exact same number of atoms. They've got the same molar mass, that means. They've got the same shape, pretty much, so the dispersion forces are going to be similar. Now, one is polar and one is not. You should be able to see this and say, oh yeah, this is going to be polar, this is going to be nonpolar. So this is going to experience some dipole forces. But a huge difference is that this, in the ethanol, the hydrogen is bonded to an oxygen here. And here, the oxygen is bonded to 2 carbons. And so here, the ethanol can experience hydrogen bonding between ethanol molecules. And if you remember, if we go back to here, remember when we were looking at differences in dipole-dipole forces, this is only about 10 degrees higher than this. So while that is definitely causing a change in boiling point, it's not an enormous change in boiling point. If we go back here, though, this is a lot higher. I mean, that's almost 100 degrees higher than this one is. Actually, it is more than 100 degrees higher. Mental math is not my thing. But you can see, because of the hydrogen bonding, that's going to cause ethanol to actually be a liquid at room temperature. So ethanol is alcohol, and it's a liquid at room temperature compared to methoxymethane, which is going to be a gas at room temperature, all because of where the hydrogen is bonded. The hydrogen here is bonded onto an oxygen, whereas here, all of the hydrogens are bonded onto carbons. So again, these are the 3 types of intermolecular forces that we're looking at: dispersion forces, dipole-dipole forces, and hydrogen bonding. And as far as which one is weakest compared to which one is strongest, this is the order in which they go: dispersion, dipole-dipole, and hydrogen bonding. Please feel free to put any comments you have on the comments page of YouTube, or you can ask them in class. For some reason, I don't see where my little thing is to end the video, so I'm just going to say you can press stop right now because it might take me a second to actually stop the video. Have a good night.